So the power rule then. We can use the power rule to integrate over any function on the form ax to the power of n, where a and n are constants. The important thing here would be that n is different from -1, and n is also an integer. So this thing here, this is the set of integers. So n is an integer, so it needs to be a whole number. It could be positive, it could be negative. So here comes the power rule then. So you have an integral over a function that looks like this, and I'll give you a couple of examples afterwards. Okay, so when we integrate, we can use this formula here, a x to the power of n plus 1 divided by n plus 1. Plus c. This is the form that you'll find it in the formula booklet. So you can see that here. I don't think it's the most user-friendly version of the rule, so I'll just give you I mean, it's the same rule, but it just looks slightly different, and it's easier to use that way. So we can write this as ax to the power of n plus 1. So it's like the opposite of differentiation, where we had to lower the exponent, but now we raise it. And then we can multiply this with 1 divided by n plus 1, which is going to be much easier in many cases. This means exactly the same thing as the thing up here. It's just easier to use. So let's look at some examples. So, for example, x to the power of 5 divided by 4. So that's our function, and we want to integrate over that function. Well, it could be useful to just rewrite what we have before we begin. So this actually means x to the power of 5 multiplied with 1/4. And now it's on the form that we have in the formula, right? So we have a number a multiplied with x to the power of something. So when it's written as a fraction like this, it's slightly unrecognizable. So we want to be able to see what is a, and so on. And then we can use the formula more easily. Okay, we take x to the power of 5 plus 1, so we had to add 1 here. And then we have Then we have 1/4, but we want to multiply that with 5 plus 1. So the result here is going to be, okay, 6 divided by 4. And then x no, sorry, my mistake. Like this. Okay, 1 divided by 6. Yeah. So we have 1 divided by 6 and multiplied with 1 divided by 4. So that's going to be 1 divided by 6 times 4, which is 24. X to the power of 6. And we can rewrite that. Of course, we have to add this invisible c here. We can rewrite that as x to the power of 6 divided by 24 plus c. So that's our first example. Look at one more example and then one final example. So 2 more examples. Okay, we are asked to integrate over the function x squared divided by 2 plus 3x minus 1 dx. We can start by rewriting it. And when you have several terms in a function that you want to integrate over, you're allowed to split it up. So the integral over this function, it turns out to be the same. And I'm not going to prove that here, but it turns out to be the same as the integral over the several parts. So we can just split it up like this. Right, so we just integrate over each term one at a time. And it's exactly what we did when we differentiated the function. We could differentiate one term at a time. So we can also integrate over one term at a time. So when we do that, okay, this first one, we know that this is going to be x to the power of 2 plus 1, so that's 3. And this is multiplied with 1/2, but we also want to multiply it with 1 divided by 2 plus 1, so 1/3 plus c. And this is going to be 1/6 x to the power of 3, or x to the power of 3 divided by 6 plus c. So we just need to remember to add this plus c every time. I keep forgetting it. But, yeah. And that's not the final answer, by the way. So a bit too quick here. So we have to deal with the whole thing, of course. So now we add the second term, this one, 3x. We want to integrate over 3x, so that's x to the power of 2. And then we have 3 multiplied with 1 over 2. And the last one is just x, because when we differentiate x, we get 1. And then plus c at the end. And we can rewrite this as x to the power of 3 over 6 plus 3/2 x to the power of 2 minus x plus c. Third example. Integrate over the function 4 divided by x squared dx. Okay, here we have x squared at the bottom of the fraction here, so it's the denominator. And we always try to rewrite this so we get it on the form ax to the power of n. So we need to make sure that it looks like this. Yeah. And what we have here is the same as for, if I multiply with x to the power of minus 2 here and here, we get x to the power of minus 2 divided by 1. So we can just write this like this. Yeah. So we have to use the rules of power numbers, the rules of exponents to get from here to here. Now, we just use the power rule to integrate over this. So x to the power of minus 2 plus 1, we multiply with 4, and then 1 divided by minus 2 plus 1 plus c. And this turns out to be, okay, we have 1 divided by minus 1 multiplied with 4 x to the power of minus 1 plus c, which is the same as minus 4 x to the power of minus 1 plus c, or we could write this as minus 4 over x plus c.